Good afternoon or morning to all. On behalf of the Exit Swindom International Network and the Instituto de Ingeniería de la UNAM, I want to thank you for your presence in this webinar, Facing Climate Change Towards Sustainable Coastal Cities. To start, I would like to give the floor to Professor Rodolfo Silva from the Instituto de Ingeniería for him to open the webinar. Please, Dr. Rodolfo.
Thank you, Valeria. Welcome everyone to this series of conferences that are being held as part of the activities of the Exit Swindon Network. Together, the many small efforts of all of us who play a part in this family will help us to share a better world. The aim of fostering a more responsible use of water and energy, of recovering and conserving terrestrial and marine ecosystems for generations to come will change our collective future. I would like to say thank you very much to our 6 colleagues who will be participating today and tomorrow in this webinar. It seemed a short time ago that I met them as students. Today, they are our present and our future in these various disciplines. Thanks a lot. Over to you.
Thank you, Professor Rodolfo. And well, we will start with Alejandro Astorga. Alejandro studied his bachelor degree in geomatic engineering here in Mexico at UNAM. And during his master's, he simulated coastal processes on the reef degradation scenarios for his research. Currently, he is a PhD candidate in civil engineering in the University of Queensland, and his research is focused on the role of fringing reef systems on beach morphodynamics through controlled laboratory experiments. So please, Alejandro, if you would like to share your screen. Amalia dice Alejandro que no puede compartir la pantalla. Luis, no sé si lo tienen habilitado. Para su video también. A ver, just a second, please. I can share my screen, but he won't be able to speak.
Hello?
Yeah, we can hear you now. Yeah.
Okay. Yeah. Ready? Can you see my screen?
Yes. Yes.
So yes, as Vale mentioned, I'm doing a PhD in the University of Queensland, and I'm researching about morphodynamics on fringing reefs. And it's a pleasure to see that there are some people who attended to the summer school in 2017. So hello to all of you. This is going to be the outline in which I will mention some definitions of sustainable development, climate change, and coral reefs, because at the end, the webinar is related to this. Then we have coral reefs relevance and climate change. And then I will talk about the plan, the sustainability plan for the Great Barrier Reef. And finally, I will talk about a case in Mexico, specifically in Cabo Pulmo. So first, I wanted to define sustainable development because as engineer, it's not a topic that we talk about much. So that's why I wanted to see a proper definition of this. So for the United Nations, we have this a small and concise definition, which says that the sustainable development is the development that meets the needs for the present without compromising the ability of future generations to meet their own needs. And I found it kind of, I mean, it's a good definition, but for me, or at least as engineer, it doesn't tell me anything. So that's what I try to define. That's what I decided to define first sustainable, and this means the capacity of an entity or an outcome to maintain over the time. But academics apply the concept to connote a healthy economical, ecological, and social system for human development. And this can be improved and sustained. And on the other hand, we have development, which Pitt in 1999 defined it as an evolutionary process in which the human capacity increases in terms of initializing new structure, coping with problems, adapting to continued change, and attempting with purpose and creativity to reach new goals. So I find this definition really nice, actually. So in order to have a proper definition of sustainable development, Rogero suggested in 2021 that we must consider three things. The first one is the complexity of the social ecological systems by including the economic, ecological, and social factors, which are commonly known as the three dimensions or pillars of sustainable development by Atkins in 2000. And then we also have, we also need equity between and in generations. And we need feedback between the social ecological system and their surroundings. And here, I think most of you or some of you could be familiar with the Venn diagram for sustainable development, in which we have these three parts: the social and economic and environmental factors. And the social part relates with humans, mores, and values, relationship and institutions. The economical part concerns the allocation and distribution of scarce resources, and the ecological involves the contribution of both economical and social, and their effect on the environment and its resources. And for me, I mean, I did like a mix of all these definitions. So what I found, or an easy definition for me, it is this one, which is an evolutionary process in which healthy human communities can increase their capacity to initialize new structure, cope with problems, adapt to continued change, and attempt to reach new goals. And this should consider the complexity of the social ecological system by including economic, ecological, and social factors, without compromising the ability of the present and future generation to meet their own needs. So that's what I kind of find helpful for me. And now we need to define what is climate change. And according to United Nations, this is the change which is attributed directly or indirectly to human activity, which alters the composition of global atmosphere, and it is additional to the natural climate variability observed over the time. So, in other words, it's a long-term change in the average weather patterns that define the Earth local, regional, and global climates. This can happen by two processes of forcing. So we have internal and external. As external, we have the persistent anthropogenic changes in the composition of the atmosphere. And I highlight this because we have observed changes in the Earth climate since the earliest 2000 2000, no, from the early 20th century. And these are primarily driven by human activities, particularly fossil fuel burning, which increase the surface temperature of the Earth. And some indicators of these are the ocean temperature increases, the ice loss at Earth poles, and the frequency and severity of changes in extreme events such as hurricanes, heat waves, wildfires, and floodings. And yeah, now I'm living in Australia, and I mean, I'm not a parameter of these indicators, but when I came here, we had like a bad time with bushfires. And just recently, like 2 or 3 months ago, we had a really bad flooding in Brisbane, the city where I'm living. So, yeah, these indicators told us that the climate change is being altered, and these are also threat for coral reefs. But what is a coral reef? A coral reef is a tract of corals growing on a massive wave-resistant structure and associated sediments. It is built by skeletons of successive generation of corals and other calcareous reef biota. They are important because they provide several ecosystem services, which can be classified in 4. So we have supporting, because they support biodiversity, habitat, and they also support sand or sediment for beaches. Then we have the regulating services, because they protect shores. They also regulate erosion. They also have a big role in the biochemical cycling. For example, they clean the CO2. And then we have provisioning services. So they provide fishes for food, for example, or material for pharmaceutical industries. And then we have, finally, we have the cultural services. And these could be related to tourism, because they are like beautiful things that people want to see and experience. And here I show the distribution of the coral reefs in the world. They are located mostly between the tropical. They are located in the tropical areas between the Tropic of Cancer and Capricornia. And here, in these areas, we have a big population. I mean, close to the reefs. We have around 100 million people living in the first 10 kilometers, which represent the 1% of the global population. And these numbers keep increasing. Like, for example, I mean, these numbers, or this table that I show in the right, these are from 2014. So I guess now the numbers should be like, I don't know, 10% or maybe 20% bigger. But anyway, we expect to have more population. For example, close to the reefs, like 100 kilometers away from them, we have 500,000 people living there. And it is expected that in 2050 we will have 1 billion people living close to these areas. And these ecosystems are really vulnerable, especially to climate change. And for example, I mean, we expect to have ocean warming, and that means, this will affect coral reefs by increasing their mortality, the coral mortality. Also, the ocean warming will promote the coral bleaching. We will lose some of the structure of the reefs, we will have more algae growing around the reef, around the corals. So all these ecosystem service provided by them will be reduced. For example, if we don't have enough reef structure, we will lose some of the coastal protections. And yeah, for ocean acidification, we might expect to have weaker structures. The reef won't grow as, I mean, we will have limited growth of reefs. And same, we will lose some of these ecosystem services. And sea level rise is also going to affect this, especially the coral reefs will, or at least corals, they will try to find new areas to colonize. So they will get closer to the surface, or maybe they will change in latitudinal in a latitudinal way. So, for example, in the northern hemisphere, corals will move northern, and in the southern. Now I'm going to talk about the Reef 2050 long-term sustainability plan of Australia. So the main objective of this is to ensure the outstanding universal value of the Great Barrier Reef. It should continue to 2050, and also one of the aims is to ensure that the reef remains as a natural wonder for successive generations. The plan addresses the management of all values within the World Heritage Area, which was declared in 1981, and for species and habitats to indigenous values and historic heritage. The Great Barrier Reef is located in the northern eastern part of Australia, in front of the state of Queensland. It's the largest living organism in the earth, and it is about the size of Italy. The longitude of the system is of more than 2,000 kilometers. And here in this plan, the first thing they did was to recognize which pressure they have on the reef. So they have, so I did this table or this plot in which we have in the x-axis time and in the y the spatial impact. So they classify the impact in three. So we have the long-term and system-wide, which is the climate change. Climate change will affect because the ocean will be warmer, we will have sea level rise and ocean acidification. So it will affect the full system in a long term. Then we have the Then we have the immediate system-wide, which is related to land-based runoff. So this is the increase of nutrients and sediment from pesticides in the reef. And this is a big deal. For example, in Mexico, nowadays we have a lot of sargassum arriving to the shore. So that's why it's a big deal. Then we have the immediate local or regional pressures, which is the coastal land use change. And we also have this pressure that is related to direct use, like illegal fishing, incidental catch of the species, and yeah, so those kind of pressure can be managed. However, the hardest is going to be climate change, because that means that we need like an international cooperation, and it's really hard. The management of this plant consider action, investment, and science. On the one hand, we have actions, and one of these is to name a Queensland Minister of the Great Barrier Reef, reduce the tracked material in the reef, because along this coast we have several ports, and we need to tread some of these areas to allow ships to get into the port. So most of these materials sometimes were dredged into the Great Barrier Reef, and one of the aim is to reduce that to zero. Also, some of the action that they have done is to protect fauna like turtles or dugongs or manatees. An important feature of the management is the investment, and this investment is around 2 billion Australian dollars. This in the first 10 years. And something important that I noticed is that around $250 million are focused on research and monitoring, which is it's really important to evaluate the health of the reef. Also, there is a special attention on investing on improving the water quality, because that's something that can be managed easy by Australian government. And then we also have the science part, which aim is to protect the marine environment and corals, to improve the water quality, and others. Also, one of the main aims of this plan is to reach the resilience. And this is an important capacity of a system, because if you have a resilient system, it will be easier for the system to cope with changing climate. And for this, it is necessary the teamwork from scientists, communities, traditional owners, or traditional owners here. It's related to First Nation people or Aboriginal people, also industry and NGOs. And obviously, we need international efforts to reduce the carbon emission, but that's hard. This teamwork should be focused on improving the water quality, maintaining the biodiversity, and ensuring the port development. Australia, about the carbon emission, Australia has reduced the levels in the last 20 years. So at least Australia is doing something to reduce the impact. And in order to reach the aim of the plan, we have 7 themes in which we have 7 themes. So we have governance, economic benefits, water quality, biodiversity, ecosystem health, heritage, and community benefits. So the plan consider action on these 7 themes. For example, for governance, they are looking to effective arrangement and coordinated management activities. For economic, they look for economic activities within the GBR and its catchment sustain the reef of standing universal value. For water quality, they look for to improve the quality of the life, to have a better resilience on the system. And also for biodiversity, they are looking to maintain diversity of species and ecological habitats. For ecosystem health, they are looking for, for heritage, they are looking to keep the indigenous values. And in these are some of the results in 2020, in which they have done 70 actions. Only 4 of them have been completed at that moment in 2020, and 63 of them are on the track. And as you can see in the right image, for water quality, they didn't have as much action as in the ecosystem health theme, but they have accomplished half of them. So we can notice that water quality improvement is something really important for the reef. And also, as I mentioned before, the carbon emission of Australia have dropped in the last 15 years. And I'm going to talk about Cabo Pulmo, Mexico. So this place is located in the peninsula of Baja California, and it is located in the state of Baja California Sur. So this was a small town of which was dedicated to fishing in the 50s. So they were doing this activity in a small scale, in an artisanal way. Then, with the pass of the time, in the 60s, they started overfishing and bringing large commercial fleets, and that degraded the system. For the 80s, they stopped doing these overfishing activities, and they based their economy to ecotourism. And by the 80s and 90s, residents, academics started the creation of the protected area, and it wasn't until 1995 until the park was officially created by the federal government. And in 2003, Amigos para la Conservación de Cabo Pulmo this entity was created to start a new plan for management the area, and in 2009 they finally did a management plan. So nowadays this area is healthy. They have improved the they had improved the management of the area. For example, they have increased the population of fishes by 400% if we compare it with the 80s population of fishes. So in this area, they have tried to implement sustainable development, and at the moment it has gone good. However, there are many social problems or community because the management plan was mostly focused on the ecological part, and this can be improved, but yeah, it needs collaboration of everyone, and yeah, that's in summary. So if we want to do sustainable development, we need to understand that reefs or coral reefs are under a big pressure. It can be local or worldwide. We need to reduce or mitigate these pressures. we, from a point of view, we need that coastal communities identify with the ecosystem. That's something that happened here, but for example, in Mexico, I don't find that it happens in the Mexican Caribbean. Mostly because there are many people who are not from that area. So we need government, community, and private sector and academic teamwork. It is important to invest in research and also in management. And we need a constant monitoring to have indicators of the health of the reef. And we need to build resilience against climate change. That's all I have. Thanks.
Many thanks, Alejandro, for your presentation. We would like to, well, if you have any questions for him, please leave them in the chat, and we will leave them for the end of the other two presentations. So we will continue with Ana Patricia. I don't know if you have the permissions, Ana Patricia, for turning on your camera. Not yet. Luis, ¿nos pueden ayudar para que Ana Patricia pueda compartir y activar su... gracias. So I will introduce Ana Patricia. She develops machine learning methodology by using remote sensing, including field, drone, and satellite sensors, including LiDAR, SAR, and optical data applied to mapping and monitoring ecosystems. Currently, she's finishing her PhD at the Remote Sensing Research Center at the University of Queensland in Australia. So she will present us a new way to understand ecosystem structure, terrestrial laser scanners. So please, Ana Patricia.
Thank you so much, Valeria. Can everyone see my presentation?
No, I don't know.
Yes, well.
Yes?
I'm seeing a background of
okay, yes. Okay, that's what it is. Well, thank you so much for the introduction. Yeah, as Valeria mentioned, my name is Ana Patricia Ruiz Beltran, and I'm doing a PhD at the University of Queensland and at the Remote Sensing Research Center, and also at CSIRO, which is a government organization of research in Australia. And I'm also working as a remote sensing scientist in the Queensland government. So what I do as a remote sensor is that I do maps, I do models of vegetation traits. So it's very important to understand vegetation patterns, because these are controlled by physical factors, including topography, climate, substrate, type, and disturbance, but at the same time are influenced by the biota, by the animals, by herbivorous, by competition between the species. So we need to quantify these relationships if we want to understand the plant communities, but also if we want to do future plans. And as Alejandro mentioned in his last talk, the climate is changing, and so this also will change how this will impact our natural capital. So some of the maps that we currently have of vegetation traits, as for example this one, that it's height above the ground, which is basically the height of the trees. As you can see, in the Amazon it's very high, and in Australia it's very low. It's mostly desert in the center of Australia, and this is done by a satellite sensor that is in space. This is another one, a little bit more complex, which is above ground biomass. I will talk about above ground biomass most of
Okay, I think we lost Ana Patricia. Maybe I guess her internet isn't working. So
Hello.
yeah, we lost you.
I'm sorry. Where did you? Okay, I'm just gonna. Okay. Okay.
I guess we were in a previous slide.
I'm sorry. You lost me a long time ago. How do I return? Okay. Here.
Yeah, you were finishing there.
Okay. Well, this is a map of a vegetation trait, which is tree height, and the other one, which is a little bit more complex, is above ground biomass. And I'm going to be talking about this physical trait. But what I was saying is that if we want to do all these models at like global scale or regional scale or even really local scale, they are models, so we need ground measurements, which is calibration and validation data sets, right? So typically we go to the field and we do some measurements of the vegetation. For example, we do diameter of breast height, like to see the size of the tree somehow. Also, we can take some hemispherical photographs to see how much leaves and wood there are, because they interact differently. So having this difference is really important. We also take measurements of the height with some laser rangers, which is not very accurate, but it's what we have. And we also can measure with spectral signatures the photosynthetic activity that is going on in the plants, and then we can relate this with carbon production or just vegetation production. Although these measurements have been used a lot to calibrate and validate models, they're also biased somehow, and we need to improve them. So one of the things that I wanted to talk about is above ground biomass, which is what I'm doing, because there's an increasing need for carbon accounting. So already Alejandro mentioned climate change. So, well, the industry, the forest, forest degradation, the bushfires that we have, all these processes emit CO2 to the atmosphere, but at the same time, they are resolved by the forest. So if you want to understand climate change, carbon accounting needs reliable and accurate data. So also right now there exists the carbon offsets in the market. So we need really accurate data. So this can be a little bit more, they can have a little bit more credibility. So what I'm trying to do is to provide a verifiable method that will help us to understand how accurate carbon storage estimations are. And I'm trying to fill this gap. So above ground biomass, what it is, it's basically the weight of the trees. So it's all the living vegetation above the soil. So the stem, the branches, flowers, the bark, seeds, foliage, everything that it's above the soil is above ground biomass. And what it's below ground biomass, like the roots. So just let's keep it simple. So what are the calibration and validation data sets that we have to estimate above ground biomass on the ground? Well, there's the direct method, which is basically cutting a tree and try the woody biomass, and then you measure it. But of course, like, this is very unreliable to do it at a large scale. So what we do with these trunk trees is that we develop allometric equations, which are empirical equations that relate a tree metric with the weight of the tree. It could be like the tree height, the canopy diameter, or diameter of breast height, which is the one that we mostly use because it's really, really easy to measure it. But this method has a problem, is as we cannot, it does not account for the differences that we can have between between different environmental conditions. So, for example, we are all humans, and if we all measure our belly, we are not going to know how we weight, right? Because some people live very high altitudes, low altitude, so we are different, and the trees are the same. And another thing is that also environmental conditions change, but also, as I said, the trees interact with the environment and the ecosystem there, like everybody. So also this makes that trees have different shapes, even though they are the same vegetation types. And also, diameter breast height, even though it's very easy to measure, does not represent accurately the above-ground biomass. This is an example of a site that it's here in Australia. It's an experiment where they're pumping some CO2 to see how the trees change over time. And if you can see in the stem of the tree, you will see that along the years, this measurement is not changing that much, but it's changing, but the height of the tree is changing quite drastically. So if we were using only diameter breast height to estimate the above-ground biomass, we will be incurring in many sources of error. So the problem is that this is what we do in the field as a calibration and validation dataset, and then we extrapolate this to big models. So what are we doing? Well, a method that is increasing popularity is terrestrial laser scanners. The use of these scanners, and these scanners uses laser that acquire accurate, dense, three-dimensional point clouds, and we use it with the trees. I've seen many engineering applications of this, but a couple of years ago, someone was like, okay, let's put in the trees and let's create these three-dimensional models of trees. So with these three-dimensional models of trees, we can not only estimate tree height or the volume of the tree, but also the number of branches, the diameter of breast height, surface area, cone diameter. We have a lot of information for every tree. That also this tree that I'm showing, it doesn't have the leaves, but we can also have how, like, we have a quantity of how many leaves they are, and well, it provides a lot of information that we as humans going to the field, it's impossible to get. Next slide. Okay, so my goal is to contribute to carbon storage mapping by improving existing and developing new methodologies. But an objective in this chapter I'm presenting you is to compare above-ground biomass measurements at a broad scale by using terrestrial laser scanners and allometric equations in, of course, Australian landscapes. So basically what I do is I estimate the above-ground. I went to 3 plots. To 3 sites in Australia, and then I scan these sites with the terrestrial laser scanner, and with the wood density value, once I have the volume of each tree with the wood density value, I estimate the above-ground biomass. And I also measure the diameter and breast height of each one of my trees. And then with the allometric equations that are on a database, then I have the biomass of these two methodologies. So my study sites are, the one it's Litchfield, which is a savanna ecosystem. The other one is Samford, which is a open woodland eucalypt forest. And the third one is Eucarupta, which is a wet eucalypt forest. So one funny thing about Tumbarumba is that it got burned by the bushfires. So right now, there's some tricky things, but the thing is that it got burned where the bushfires were quite big here in Australia. So these are 3 contrasting different vegetation types, and also they have different carbon content. So what we do is that we take a vegetation point cloud, and then we process this point cloud using a deep learning algorithm that segments the points into leaf and wood classes. And at the end, we only have what we are interested in, the wood and biomass, and then we match this information with satellite data. So as an example, here you can see the tree vegetation types. Like if you see the pictures, they actually don't tell you much, but now that you see the data and everything is on the same scale, you can see how different are these ecosystems. And also we have the information about each number of the trees and the leaves. Here in Tumbarumba, the vegetation changed after the fire, so I think it's really nice that you can see how the model shows the data, the vegetation in the stems versus the tree, the real image. You can see here, for example, that does a little bit of overestimation on the leaves because there's no leaves actually in reality. But these methods are, well, currently improving, and a lot of people is just focusing on doing, you know, an algorithm to segment the trees. Other people is doing an algorithm to just separate leaf in the stem, and other people are doing like the reconstruction of the tree. So it's a lot of teamwork, and it's something that it's currently, well, in progress. This is another example. I picked some of the trees, like the biggest and the smaller tree of my plot, and then you can see the differences between also the tree sites. Like Litchfield is a savanna. The trees are not really high. Tumbarumba, it's wet. Trees are, well, quite high for Australian ecosystems. And also some errors that we get in the tree segmentation that we need to improve, but, well, it is what we have for now. So the difference that I found between each site is that for most of the sites, I had less biomass by using the allometric equation and more biomass estimations by using the terrestrial laser scanner. This is the first time that we are trying to do this at the plot scale. There's many research that's shown that terrestrial laser scanner, using it for estimating above ground biomass, it's way more accurate than allometric equations, and the allometric equations usually underestimate the above ground biomass. So having this, it's well, this is just a comparison, and then the question is like, well, what's the true, right? Because if you want to know what's the true data or the true values, we need to chop the trees, and that's yeah, like these sites are very protected, so it's going to be impossible, and we don't want to do that. But to have into account that there's differences, and these differences, when you make maps of this, you, as I said before, you're extrapolating this information. So why is this related with coastal ecosystems, right? Well, we have scanned some mangroves as well, and also salt marshes, but I don't have the scans. So we can see also the structure of the mangrove when there's low tide. And also this is near Brisbane, but this is another mangrove site that I haven't processed yet. But it's a little bit up. So this is like dwarf mangrove versus another mangrove forest, and we also have these differences. And right now, I want to test if I can run these algorithms of these ecosystems and see what information we can have, because usually the methodologies, like I think from 1 year ago, they were only focusing on segmenting a tree and then estimate all the parameters from the tree. And the methodology I'm using now first separates leaf from wood and then does the estimations at the plot scale. And this is very tricky with mangroves, because mangroves, you know, they have a vegetation structure that it's I don't know, quite complex, so to say. And right now there's some research, for example, about how the wind speed change, right, based on the tree, because wind plays a role. And then I was thinking, well, water also plays a role in mangroves, and mangroves, you know, provide protection. So if we want to do some predictions or some models, maybe we can use this data, right, to fit these models and understand what is the role or what's the degree of protection of these mangroves, and then future scenarios. Right now, for example, we just put a tower in one of my study sites, so we are trying to relate, the wind speed based on the height of the tree and the complexity, of the plot. In this, this helps on see how the bushfires can spread. So it's just a rough idea, and I wanted to present you this because I want to get more ideas. I'm not an engineer, and I'm not a coastal engineer, but I think there are potential applications based in coastal ecosystems that can help us. Thank you very much for your attention. This is just one little chapter of my PhD. The other chapters will now include including the integration of these datasets with drones and spaceborne LiDAR and Sentinel data, but that's for another talk. Thank you very much, and I'll be happy to answer any questions or comments.
Thank you very much, Ana Patricia. We will have time at the end also for some questions. If you want to leave them in the chat for her, please do. So we will have our last presentation for today. Si nos pueden ayudar con el permiso para Edgar. Thanks. So now we will have the talk from Dr. Edgar. He is a researcher in the Instituto de Ingeniería de la UNAM here in Mexico. He is responsible of 2 wave rooms at the Institute, and he is also responsible of coastal and ocean fieldworks performed at our group. His research topic interests include coastal processes, numerical modeling of wave conditions, and structure for coastal defense. He will present us new and traditional challenges for coastal protection. Better questions lead to better solutions. So please, Edgar, you can share with us your screen. You have your micro off. We can hear you. I see you talking, but
so you should.
Yeah. Now we can.
Thank you. And now let's see if I am capable of sharing the screen. Maybe I think that you should be seeing my first slide. Yes.
Yes, we can see your.
Okay, thank you so much. So clearly, there is an age barrier here, and my 2 previous presenters are young and they easily use this stuff, and it's not my case, clearly. But I am very happy to be here, and I was watching the talks by Alejandro and Ana Patricia, and I couldn't stop reminding them as a very young students, and watching now them how they have grown and how they understand actually. I think that much more the scientific and technical stuff is quite interesting, and it is also very satisfying to see the people growing and at least think that we are contributing to produce better scientists and better engineers and better technical people in general. So thank you for the invitation. It is very good to be here. It's very interesting to see a lot of names there in the list of attendees, which are people that we have seen for a lot of years, and we love you all, really, we do. And this talk that I prepare is not so, let's say, technical. It's not my idea to go deep into some technical stuff, but instead of that, I was thinking on inviting you to think a little bit on some issues. An issue that I think is very important, and I think that instead of going into some equations or some difficult stuff for a Thursday evening in Mexico, at least, my intention is to invite you to think a little bit on our study object, and also considering that we are all working in the framework of climate change. And sometimes we have to think and rethink some issues that we may have thought earlier that they have already been solved, or that there is not much more to do around some topics. And then we discover that we have to continuously go back and rethink the things and put all our knowledge all together again. So why to go back to coastal protection? Coastal protection has been performed by human beings probably for more than 1,000 years in different scales and for different activities. But every time we are going back to rethink and to, let's say, develop some philosophy around coastal protection, because we need it. We have actually a very important number of people dependent on coastal protection, and in some literature they say that this number of people will triplicate in the next 10 to 15 years, and if we accept that we are going to experience almost all around the globe a sea level rise, probably this number of people that is dependent on coastal protection will grow even more. So it is important to think again on how we do it, why we do it, why we need it, and what are we doing with our coasts, locally, obviously, and globally also. So I put this image. Is not something that you could not see in any book or in any literature available about regarding so much topics, including coastal protection. But I wanted you to think again in how are we using our coasts, and not with the idea of changing the use we do, but probably how much stress we are inducing to our coasts, and think a little bit that the stress is not only, let's say, urbanization and transport and communication infrastructure or tourism infrastructure, but sometimes we also induce some stress making big efforts regarding conservation and regarding trying to get to a state that we have thought that is the ideal state of some coast, but sometimes we are not thinking really in the natural cycles and in the recovery of the naturality, not only in the coast that we want to see because a paper or a book said that that was the best state for any coast. So that is why I am inviting you to think again in which are really the causes for coastal degradation and which are the main risk triggers actually in our coasts. And I think that we can group them into 4 great groups, which are, as you can see in my slide, obviously human activity, sea level variations, hydrometeorological issues, let's say hurricanes, storms, but also fluxes that come from land, such as rainfall and the use of sediment in the higher part of land that prevents it from coming to the beaches, and also I wanted to group some triggers into a geological group, where we can put, let's say, earthquakes, tsunamis, tectonic movements, which also put in risk the coast, and it may be sometimes it may occur in a very short period of time. So regarding these triggers, one thing that we should take into consideration is I think that these 3 characteristics, the influence area of each of the groups, the speed of occurrence of each of them, and the ability of the coasts to adapt or recover after the event or the let's say the action has happened. No? So I try to reflect some of the experience we have acquired in these years and classify the triggers, the risk triggers of the degradation causes for the coast into trying to reflect how we see them after some experience. And of course, the geologic events and also the sea level rise, or not only rise, but also some sort of risk could be present if the sea level should decrease instead of rise, but let's say the sea level variations. And of course that it's interesting to see that the anthropic actions normally are not so extended in space. But as I try to put in the second pie chart, the occurrence speed of the anthropic damage to the coast is the one that occurs in less time, while some other natural or almost natural effects occur with some time. I mean, it can be also geological time. And it is also interesting that many of the human interventions may be recovered or may be turned back in many situations. So we have to think on how to do it, and this means that any alternative or any rationale that we use to define and to design coastal protection should respond to the specific local needs and constraints of the place. And this means that we have to, before trying to design or before trying to solve a problem, we have to understand a little bit more of the problem. And this is where I wanted to get you all to think. And I will show you the real problem. Obviously, this is a joke. And I am sure that you have seen this chart quite several times. And my idea is to make you think a little bit about this, because seems to be a simplistic way to fix something, but from another point of view, probably the detail is not in the simplistic way of solving things, but in being incapable to produce the correct questions. So what we can see here is a very simple question, a very generic question that probably makes the technician to look for a very simple answer. So probably we should think on, are we not being able to make smart questions to solve coastal problems? And now, after the small joke, I want you to see this slide and try to make you think that we are seeing the same thing. Here we are watching a very simple question which has been solved in a very simple way. So this idea that many people have, probably some people still have it, that engineers come to the beaches to destroy them instead of protecting them, or instead of making some good solutions or something that could be considered natural or optimal, or let's say environmental friendly. I think that sometimes it's not only, or we should not only blame the person who decided to construct things like the ones we are seeing in these pictures, but probably also the person that made the questions did not took the time to make this the questions, the complete questions, let's say, in a way. So I want you to get your minds back to the joke chart, and then see this slide as the same chart and the same problem, which is, I should say, a non-technical problem. And then digging a little bit into the education literature, I found that they have a lot of information regarding practices and techniques to show people how to make what some authors call smart questions or effective questioning practices. And what is very clear is what we should not do when stating questions. And the main points are avoiding being superficial, avoiding asking too few questions, avoiding using the wrong language, which is a problem because you are working with decision makers and engineers and biologists and probably sociologists. The language is a problem, the language is an issue, but if everyone speaks his own language, then everybody is using the wrong language because there is no communication. And well, I saw in the list of attendees Deborah Lidgo, who is, I think, an expert in detecting people using the wrong language. Also, sometimes the questions are poorly expressed, and we should avoid that. And also, trying not to do questions which have a simple answer of yes or no. If you remember the last slide, the previous slide, the question was, can you stop coastal erosion? And of course, that the answer could be, yes, I can. But if that is the only question, that would be the only answer, and I can feel somehow free to do a lot of things that may not be optimal for any side or whatever. So also the education people have developed a lot of, I wrote here types of questions, but they also call them questioning flow. And they use a lot of, there is a lot of theory behind this, but the main types of questions are those that are convergent, that is, that you are looking for a solution which is unique for all the questions, or a divergent, which is different solutions after having asked a lot of questions. Focal questions, which are related to one topic, let's say in our case could be only coastal erosion, or it could be only ecosystem restoration. But if we focus only in one topic, then we have to use, or we could use this kind of questioning flow, a brainstorm, which I think we all know it very well, and the funnel type chart, which is making a lot of questions, trying to get a single solution related to all the questions. So whatever type of question we select, we have to intentionally look forward to get the best solution. So to the original question of, can you stop coastal erosion, or can you protect a segment of coast, we can add several more questions, trying to improve the solution as we improve also the concept that we have of coastal protection. So one first question is related to, can you do it without damaging the neighbors or the beaches that are adjacent to the one that you are trying to protect? And of course that the answer, well, it is interesting to state here that we used to say in civil engineering that technically everything is possible. You just have to ask me to do it and pay for it, obviously. You know? So to the question of can you do it also without damaging the neighbors, the answer is also yes. And the path to this is first of all widen the study areas. This image, I don't know if you can see my pointer, but this image at the left side is an example of a project that we made in the Mexican Caribbean some time ago. But the interesting thing here is that the beach that we were trying to protect was relatively small. It was no longer or no larger than 1 kilometer or 1.5 kilometers. And we decided to extend the study area to what we understood as a littoral cell in order to be able to identify the possible interaction or the possible effects of a proposed solution in places that are communicated in sediment transport and hydrodynamics terms, and also morphologically. So the idea is not to forget that all that we do in the coast is going to have an impact and an effect, but probably sometimes we are forgetting of considering all the area that is really connected to the place we are trying to protect, or in which we are trying to make an intervention. And also we have to think in placing, if the solution includes placing any barriers, instead of placing them as straight as you can see in the upper picture, try to make some strategy to produce not only a natural sediment transport, but also trying to reproduce some natural shapes in the beach, so that afterwards the solution can tend to be self-sustainable. So we can protect the places without not damaging any adjacent place. Then we could also add another question related to protect the ecosystems. Why do we want to protect the ecosystems? Well, first of all, because all the ecosystems, all the coastal ecosystems, in the end are connected between them. The connection can be biological, or the connection can be physical, or the connection can be chemical. But there is a connection between all the ecosystems, and we should avoid breaking that connectivity, because we would impact not only a small place, but also the places that are connected. So this is more or less related with the other question, but not focused only on, let's say, do not producing erosion in the adjacent beaches, but now the idea is also to protect the ecosystems. In the case of Mexico, of course, some of the most important ecosystems are the coral reef, are mangrove forest, are seagrass patches, and also the dune and beach continuum that also should be protected, and its natural cycles should also be let to continue without severe interruption. So again, the answer could be yes. And what could we do to protect the ecosystems? Probably to find better places to put some structures, or not putting structures, but working directly with the ecosystem. So we can also do that, and we should answer positively to this question, or to this idea. Another question that we could include into this question, or into this group of questions, or as I was saying some slides ago, into this question flow, is well, now can you provide some environmental services? And also here the answer is yes. And I don't want to get misunderstood here. I am only placing some examples, but of course that you can find and also think in a lot of solutions different from what I am putting here. But I am trying to get you through some examples just to continue with this reflection about coastal protection in the face of climate change, and in the face of this probably incremented or increased needs for protection that we will have in the following decades, let's say. So can you provide environmental services? Yes, we, in our specific case, in the Engineering Institute at UNAM, we designed this modular element for the creation of artificial reefs, in which we looked for a structure that may fulfill a lot of functions, or as much as possible functions, trying to reproduce the benefits that the natural reefs can provide to the beaches and to the ecosystems. So you probably, I mean, I don't have to go into the detail of what are environmental services and what kind of environmental services exist, but you can always think on food, on habitat, on recreation, and things related to that. And we found that this modular element that we designed could fulfill at least protecting the beach, which is, I have to say, which is in all this context is the main function. We could, I mean, it would be a terrible mistake to try to mimic a reef or try to give habitat or food or so, and forget about the principal or the main question, which is, can you stop coastal erosion? So we have to stick to coastal protection and then look forward to the other benefits. So from all the functions that we could find that this kind of structures could give or could provide, we again make some grouping, and we separated them into hydrodynamic function, morphologic function, and ecological function. So if a structure is able to provide or to have at least a good performance in 1 or 2 or 3 functions, then we can say that we are providing some environmental services, and as long as we can improve the performance in all the functions, we can say that we have a better solution. In the way that we were working with the structure and with the functions, we designed a simple index made in the shape of a trilemma, or which is made from 3 elements, and this is a 3-part index in which we are evaluating at the same time the morphologic, hydrodynamic, and ecologic functions of the structure. And if you see the triangle that is painted in gray, that could be the ideal artificial reef, which is the one that has the highest values for the 3 functions, and within it you could find a lot of possibilities of artificial reefs working better in hydrodynamics or in morphological terms or in ecological terms. So you could have a lot of triangles that may let any user to compare and evaluate the performance of any artificial reef, or even not only artificial reefs, but any coastal breakwater. So this is only an example of a way of improving the solution into providing environmental services, and also, well, a simple way to compare between the different solutions. Then the next question could be, I talk about protecting ecosystems, but now we shift a little bit our thinking, and now we say not only protect them, but use them or even mimic them, so that we could be able to, if we can use nature, then we can move into what some people name living coastlines. But if we are not able to use the nature, we can mimic the nature, then we can have, let's say, we can discuss a little bit about that, but we can move on to nature-based solutions, not in the sense of using living things, but in the sense of mimicking the function. And as you can see in the bottom part, this is a coral-shaped element that we also designed recently, or more or less recently, to provide not only coastal protection and not only habitat, but also the idea was to put there something that could also geometrically resemble a natural reef, and try to see how it works. We found that it was very efficient in controlling wave energy. It resulted in a very dissipative structure, and we are waiting for having some funding and other things to get ready so that we can test them in a real situation, so that we can evaluate in terms of the previous slide, that we can evaluate really the ecological function and say and see if it is really colonized, and if food chain is developed around it, and we have still to make those tests. But in terms of morphological and hydrological function, we found very good results in an element that is clearly mimicking nature. And some other ideas, of course, we can think on reproducing some mangrove forests. This is a very simple experiment we did recently, and in which we are trying to parameterize the wave damping produced by the mangrove forest of different sizes and densities and on another characteristics. So we placed something very simple to be able to have reliable measurements. And of course, using vegetation, using oysters, and a lot of solutions that you can see elsewhere or in a lot of places in the literature, makes us to be able to also say, yes, we can stop the coastal erosion or degradation. We can avoid damaging the neighbors. We can protect the ecosystems. We can provide environmental services. We can use and mimic nature, and we could still add more questions to this. Can you also improve people's life quality? This is not so common, and you won't find a lot of works in this topic, but in some places of the world, at the same time that coastal protection is provided, also the surfing areas are being enhanced so that the surfers can find better waves and that they can make some their sports and their activities, and at the same time the coastal protection is provided. And this image is interesting because if you see the photograph in the bottom right part, there is a small salient of sand there that is produced by the reef that is also generating these waves that are very interesting for surfing. So yes, it can be done. We can work into people into a social benefit for the people. This is a report of sports activities in New Zealand, and those numbers are the population. They are quite large for New Zealand, but of course that one same person can do several activities. But these are some records of an increase in sports activities related to coastal protection in New Zealand. So at least, which could be very interesting for a country like Mexico, at least one benefit for the society is that they are making more sport than they did before the coastal protection was built there. And of course that in some places also the coastal protection can induce benefits for the economy, for the business of the people that have some activities or economic activities in the beach. And in some places there are reports of people improving their incomes because of coastal protection. So it is possible, and we can do that also. Another interesting topic that is growing very fast is can you protect the coast and also provide energy? And nowadays the answer is more evident that it can be done. A few years ago we did this research in which we placed some idealization of wave energy converter farms, and we tried to investigate a little bit the response of the beaches close to the farm and how one could see their role as coastal protection measures together with the possibility of harvesting energy. And well, we did, as I said, we did this some years ago, but actually there is plenty of literature and books, not only papers, but books, and a lot of work is being done regarding this hybridation of coastal protection measures with energy, or at least wave energy harvesting. But I have seen also some, not only for wave energy, but also for current energy, that people is working on this combined answer of protecting the coast and providing energy. So it can be also done. And somehow related to our topic, or to our central topic of this webinar, can you consider climate change? Well, yes. Sometimes climate change is considered in the shape of upgrading breakwaters. So the people is analyzing the failure modes, the actual failure modes of some breakwater, and then they use some wave and sea level rise predictions in order to recalculate these failure modes and then design the upgrade that any breakwater would need to resist these new conditions, or these worsened conditions. But at the same time, there is a lot of people working in structure design, thinking in climate change from the beginning. So nowadays, some of the designs are not made only for the historical conditions that have occurred in a place, which is the normal technique we use to use historical data and then perform some statistical analysis to get values with some return period or something similar. But now what the people is changing a little bit to do is to predict or use predictions for climate change in terms of waves, height, wave period, wave direction, and sea level rise. And then they are starting to design from the beginning, considering that the loads that the structure have to resist are not going to be stationary along the life cycle of the structure. So yes, there is also a way to consider climate change and advance and answer that question. Then, well, we can add a lot of questions, but then there's an interesting point in stopping and say, could you do it all together? Which probably is the ultimate question. And the answer should also be yes, but something that I have learned from my biologist colleagues, and that has become almost a bad practice in myself, is that sometimes you have to answer yes, but it depends. And in this case, it depends on what do you really want the coastal protection for. So maybe you don't have to answer all the questions positively, because probably the answer for some of the questions is not necessary for your specific application. In this case, I am putting here this framework that we thought a few. I was going to say a few years, but it really was a few months ago that we thought on this framework, which is called DESCR, because of drivers exchange, state of the environment consequence and responses, initial letters. And the idea is to develop an analysis methodology which is not linear in terms of the path that one should follow to get a response, but that it is more like cyclical or might have some loops that would make you answer a question, then think on its consequences, and then rethink if those consequences are the ones you are looking for. So yes, all these, let's say, all these considerations can be taken together, but it should be well thought before, not to produce solutions that take into consideration things that are not really needed. So what is the next step once that we have more or less shown that we can do whatever we are asked to do, to set priorities? And the priorities should be set specifically, or I would say site specifically. Each site should have different priorities depending on, first of all, and this is something that I always say to my students, you have to think, what do you want coastal protection for? You cannot necessarily have to solve all the questions or to solve all the problems that a coastal area may have, but you have to try to solve the real problem you have found, or the real problem you have been called to solve. Sometimes, of course, one can say, you called me to solve coastal erosion, but you have a problem that is more important than coastal erosion. Or sometimes we have said to some people, your problem is not really coastal erosion, so you not need to stop coastal erosion because you are not what you are seeing is not coastal erosion. So this is the thing of setting priorities, and the questions that we do, the questions that we ask, should lead to set precisely also the priorities for our coastal protection work. So, of course, taking again some classification, we already had the hydraulic, the morphologic, the ecological, and now we can include the social aspects that one could solve with one single coastal erosion, coastal protection measure, or not. We don't know, and depends on the site. And I am going to try to explain a couple of examples. Let's say that our interest for some project is wave reflection, and we have to ask the questions related to wave reflection. Why would someone need wave reflection? Well, because they want to have a beach with a low wave attack, and they don't want to, they don't have space to put a very large coastal structure, so that the friction and the braking and the porosity will not help because there is not space. So we have to stick to wave reflection. If we stick to wave reflection, we probably won't be able to trap sediment, because we are going to have a very chaotic state, and waves would be higher than the original in the reflection part. But we may gain dry beach, and on the others probably, if we are to produce a coastal measure that is related to wave reflection, the habitat service would not be so efficient because we don't have the conditions. Probably also we don't have to answer a question regarding restoration. And if we are talking about wave reflection, probably some energy applications would not be compatible with this, and maybe we won't impact a lot in economy. So if we have some constraint, then also our questions are also limited by these constraints. And just to see a second simple example, if we are thinking on wave dissipation, then we have to probably cancel another hydraulic functions. Maybe we want trap sediment, but we could be conserving the dune or stabilizing the beach. If we are able to put there a good system when we are dissipating waves, we maybe the element that would dissipate waves would also convert some energy and then impact economy. So there are a lot of possibilities and a lot of connections between all these, which should set the priorities for the specific coastal protection strategy design. And as you saw here, I started with hydraulic constraints, but you can start with ecological constraints and then set the priorities around ecological or around the social aspects. So this is quite, or this could be quite large. So definitely we are on the need for guidelines that could help us make smart questions and also find the better solutions. Now, the world is changing, and we are facing a lot of different situations regarding economy, regarding the climate in the planet, regarding the customs and the uses of the coastal communities, which are also shifting. They are not always the same. So there are a lot of questions that we could add to our original path or to our original flow. Related to garbage, I think that tomorrow we will talk about the garbage and plastics, how to include in the coastal protection long-term cycles, natural or human-driven anomalies. And here I am thinking in things like the sargassum arrivals in the Caribbean or some other things that may be natural or human-driven, but can be considered anomalies. And questions can arise related to coastal protection in the presence of those anomalies. Plagues of different species, animal or vegetal. How to include these coastal protection alternatives with ecosystem restorations or with economic improvement or with the smart cities development or with a circular economy. So we can face in the next years a lot of questions that we will have to answer. And finally, most of this comes because, as I was saying at the very beginning, there is a lot of human dependence on the marine ecosystems, and this dependence is shifting into different possibilities and into different ways of seeing the coasts. I mean, as long as more people live in the coasts, then we are facing more points of view regarding the coasts, and probably more questions should also arise. So we have dependence on marine ecosystems for food, for economy, and the last map is the places in the world that depend clearly and for their survival depend on coastal protection, and this is going to increase with time, and not in the long term, but in the short and mid term, we will face all that. Finally, some conclusions. The art of effective questioning should enhance the technical solutions. The smart solutions can be provided if the correct questions are asked, and of course that we need interdisciplinary work groups to make the questions and interdisciplinary work groups to find the solutions. And this last idea is quite important. Not all possible questions need to be answered in any time and in any situation. And just want to thank you for your attention, for being present, and I hope that, yes, I left some minutes for questions for the three of us. Thank you.
Thank you, Edgar. Yeah, we have not much time for questions, but we will start with some questions that we have for Alejandro. I don't know, Alejandro, if you can, Edgar, if you can stop sharing, thank you. And Ana Patricia, I don't know if you have your permission to turn on your camera and your microphone.
Yes, I'm here.
Well, you are already here. We have a question in the chat from Citlali. She asks, how sensitive are the biomass estimates depending on the season of the year the work is done?
Okay, that's an excellent question. When we measure above ground biomass, we don't consider the leaves. We only consider the stem. So actually, it's preferably to go to the field when it's dry season, because then there's less occlusion of the signal of the stem by the leaves. And actually, also in the government, we are quantifying deforestation among Queensland. And we also use satellite imagery that it's on the dry season. These values don't change as much. Like leaves, you can see, for example, there's this NDVI, and you can see through the year the phenology. If there's a dry year, you see clearly the signal. But in biomass, we're still not doing change detection like on a large scale. But it is estimated that you can have sensitivity every 5 years. So maybe 1 year, it's not, there won't be much difference. So maybe 5 years. So yeah, thank you for the question. It's really good.
Okay, we have another one for you from Rodolfo. He asked, how interested would you be in applying your methodology to dunes? There are groups of researchers in Mexico who would be very interested in collaborating with you.
Oh, that's great. No, I would be very, very interested. We will have to, well, see how we can take the terrestrial laser scanner to Mexico. Because I was already looking if there were terrestrial laser scanners in Mexico, and I didn't find anything. But yeah, no, very interesting, and I'm really interested in coastal ecosystems. I came to Australia to study mangroves, but you know, like I end up working with eucalypts. So yeah, you can send me an email, and happy to collaborate. Thank you.
Thank you. We have here a question for Alejandro. Do you have your, Alejandro, can you turn on your microphone and your camera? Well, I don't see him. Maybe he lost his connection. Alejandro can turn on his camera. Thank you. I lost the question. Here. From Deborah asks, in your experience, which is the main anthropic threat to coral reefs, and how could we efficiently deal with it?
Okay. Yeah. For my experience, I think that climate change effects on the reef will be the biggest or the greatest threats. Mostly because the extension of the impact of warming of water is hard to manage. So, for example, in the Great Barrier Reef, when we have this bleaching event, it was massive. So it's really hard to deal with that. And the second one is a hard question because, I mean, it's a global problem. It's not only regional. So the only thing we can do is to stop, I don't know, using cars or changing the way we move, changing the way we eat. So that could be, it's not going to be a solution, but that could help. Yeah.
Thanks. And Juan Jose asked you if you know if considering climate change, is it estimated how much coastline will be lost?
Oh, that's difficult. To be honest, I don't know the answer. It will depend on how much the sea level will rise. But there are plenty of islands in the Indian Pacific and also in the Great Barrier Reef that might be that might disappear. So that would be a big extension. But what could happen in continent is that the beach will get more dynamic and the beach is gonna go back. Because we won't have the same rate of protection of coral reefs.
Okay, well, thank you.
I do have a question for Anna.
Well, if you
I'm not sure if
yeah, we have just 3 minutes to
okay, no worries.
finish, and I will ask just one last for Edgar, if you agree. So Edgar, Victor asks how and who should decide whether a coast should be intervened. As far as I know, in Mexico, it is the government and the economic agents.
Well, thank you, Victor. This is a very interesting question. And we should be tempted to say that the decision should be taken, let's say, technically and scientifically, but it is not always the case. Sometimes it is a political decision that a specific coast is intervened, and sometimes the solution is not also selected by technical reasons, but by economic or political reasons. But in an ideal case, we should stick to a very precise diagnostics and to, as I was saying, to state smart questions in order to get the correct solution, which is congruent with the diagnosis that we have made of the beach. So the question is like this, the answer is like this twofold. Sometimes it's a political decision, but when it is possible, it's a scientific decision, and it should be like that.
Okay, thank you. Well, I guess we have 2 minutes. Alejandro, if you want to ask Anna. We have a lot of questions in the chat still. So yeah, maybe they will send them to the speakers and maybe in the chat of the Facebook post, try to respond them. But well, if you want to make the question, we have 1 minute.
Quick.
Okay. How much time do you save with this scanner, the methodology compared with the manual measurements?
You don't save any time. If you do the manual measurements, it takes you 1 day. If you do it with the TLS, it takes you 2 months, maybe. We're trying to improve, and we have to use HPCs. Now we're going to cloud computing. But that's also the other question that I would need to answer in my thesis is like, is it worth all this processing time if we want to take this at the operational level? Because right now the traditional method is quite quick, is fast, is efficient, time efficient, but yeah, no, you don't save time. But yeah.
Okay. Well, many thanks to everybody, to Edgar, Alejandro, and Ana Patricia for being here with us today, and we hope to see you all tomorrow at 9 a.m. Mexico City time.
Just one quick comment. Sorry for interrupting you, Valeria. But the real question to Anna is, how do you manage the nightmare of carrying the scanner?
I'm going to the gym. It's yeah, the weight is 25 kilograms. Yeah, that's yeah.
I know.
Well, Well, thank you all, and hope to see you all tomorrow. Have a nice.
Thank you, Valeria. Thank you for the invitation. And
Yeah,
send us
thanks.
questions by email. Bye.